I'm Lorenzo Rosasco. You'll be stuck with me for the next 15 classes. These are basically, as Tommy was discussing the first lecture, these are more or less the core material. We cover a lot of classical materials going up to more recent materials. A word about actual support. There is this mighty draft of a book, which I'm not sure is ever going to be a real book, but it's definitely a bunch of notes for you guys. And so what's going to happen is that we're going to give the whole thing to you right away. The first chapter, I'm going to try to update the notes throughout the course of the semester. And so right now, chapter 1 is good for a first read at least. And you can look at that, you can print the whole thing. You might want to go back to it every once in a while and check what is the last date on the file, because hopefully every week I'm going to update the whole thing. This is roughly covering the 15 classes I'm going to teach and probably a little more. This year, we're trying to put this course on OCW. Specifically, the 15 classes are going to be on OCW. So we actually been preparing slides, which more or less are what I write on the board. I'm going to teach the whole course on the board. So we're going to try as much as possible to also provide you those slides, which are basically a summary of the whole thing. The whole purpose is to give you enough material to study most things and also to avoid scribbling like crazy and spending more time listening. As we recommend, the idea is that you actually come in class and attend as much as possible and can use this time to understand. So I think today we're going to start, or maybe now if he has George has the computer, we're going to start to give out the material. I'm just going to repeat 2 things I said at the end of last class in case somebody missed it. So the idea of this course is to fill in what we feel to be somewhat of a gap of the current things you can, the current courses that are offered on machine learning. The majority of courses fall into one of 2 categories. One is what I would call the toolbox, the bag of tools like courses. So they go from everything to everything. Graphical model, SVM, deep networks, whatever. Okay, and the idea is just to give you, because machine learning is such a broad field, the idea is just to give you a quick overview of everything. Okay, by definition, this course is any course like this is not going to go deep in any concept. It's just going to provide you, a bucket list of all the things you might want to look before later in your life. As soon as you switch to more theoretical stuff, people typically, go very deep in the statistical aspect of the story, which is by far the most developed part of the story. And things are like Vapnik-Chervonenkis theory, law of large numbers like result, concentration inequalities, non-parametric statistics, all of that, okay? And there are plenty of courses of both kinds that are very good, okay? We didn't feel like there was a need in any extra course doing that. We can, I don't want to make names now, but, we have a few on the websites. There are many others you can look at. And, if you're not sure, you can just ask us for more. So what did we try to achieve with this course? We wanted to try to somewhat get a feeling that while machine learning is such a broad field, it's not just a list, horizontal list of things that are completely disconnected. There are actually a bunch of ideas. A bunch of ideas that you can follow throughout different fields. So if you do graphical model, regression, or whatever else estimation, you typically have to deal with certain basic ideas. The fact that the data might be a lot, but not be an infinite amount. That might be some notion of noise. That you need to trust the data, but up to a point. That if you want to get everything out of the data, you have to make some kind of assumptions. And the broad topic, the broad pillar of all this concept in our view is the idea of regularization. An intrinsic trade-off whenever you try to learn something between fitting the data and getting something which is stable. In the sense that if you repeat the same operation a couple of times, whatever you do, the results you obtain doesn't change dramatically. Okay? So the whole idea of regularization builds around this basic idea, and we'd like to actually see how it's developed and what are some basic instances of this idea. So the idea, the goal here is to introduce some basic principles and see how they develop into algorithms. And then go in some bit of details of what we think to be some ingredients of this whole story that are worth discussing at least once in your life. So there is going to be the course is not introductory. It's not meant to be introductory. It's going to be using a certain level, assuming a certain level of maturity from a mathematical point of view. Basically, the idea is that you have to know your linear algebra pretty well, and to know basic probability theory, and then we're going to sprinkle on it a little bit of function stuff, okay? You have to know your Fourier analysis, or at least some of it, Wikipedia level, okay? That's what we're talking about. But you have to know it, okay? So you have to go back and take a look, and we're gonna sprinkle a bit more stuff. We're gonna use operators sometimes. We're gonna say what is a functional derivative, maybe, and maybe some convex analysis. We're gonna say that there is not only a gradient, but there is another thing called the subgradient that you can use where things are not differentiable. And we're gonna try to make this self-contained, and we're also going to try to bring down relatively complicated things to a layman term and so on and so forth. Clearly not making justice to any of you who want to go rigorous, and to any of you that want to just have an intuitive explanation. We're going to try to balance, we found our own balance, and we have to stick with it because there is no ideal. All right, so I guess these are all the premises I wanted to make, so we can get started. The class today and the next two classes are kind of the foundational stuff. Today is going to be about statistical learning theory. And then we spend two classes on basically introducing function spaces, reproducing kernel Hilbert spaces and alike. Not because we're in love with kernel methods, but because these reproducing kernel Hilbert spaces are not kernel methods. They're kind of the useful tool to understand when you're dealing with functions. And because the whole, 90% of what we're going to talk about is learning functions, it seems to make sense to know what a function is and how you can build spaces of functions. So that's why we spend actually two classes discussing the topic. All right. Any questions? If you have any questions now later on, just interrupt me. I usually say more stuff than is actually needed in 90 minutes, so we can definitely skip. All good so far? So there is a problem with my writing. It tends to start well and then goes in a kind of exponentially decaying quality. So, complain at some point, and usually we can let the quality go up again. All right, so today is actually going to be kind of a slow, in detail description of the ingredient of the statistical learning problem as seen in the statistical learning theory framework. So let me start just by simple stuff, that Tommy already discussed. We're going to discuss the problem of learning functions. Okay, so we assume that we have some x, some inputs, some outputs, and we want to find the function, okay, from x to y. Now, the key point in this story, and let's just make a drawing to begin with. Let's assume that the x space, which is the space where all the x's lives, is just the real line, and the y is also the real line, and we got a bunch of values, okay? So these are the x's, x1, x2, x3, x4, and these are the corresponding y's, okay? The goal is, given this data, to find a curve that describes this data. And already you can stop 1 second and wait, what does it mean to describe the data? And you can make immediately a distinction between the idea of fitting the interpolating the data and actually try to get something beyond the data, which already puzzles it, because what is beyond the data? Okay, what does it mean to do something else? We have to already start thinking that there must be something going on that we haven't described yet. And our goal is exactly doing that. We don't want just to fit the data. We actually want to do something that is good for something else. And just sloppishly now, I'm just going to write here new. We're going to get a new point. Okay, we know that we're given this today, but we also know that George is going to collect more data tonight, and he's going to provide us some new data. Let's say he's very lazy, so he's just going to get us one more. And we need to say where here we want to put our little circle. What is the correct y? Okay. Eventually, he will also spend some more time figuring out himself, because he's our teacher, what is the correct y, and then we have to figure out whether we did a good job or not. So, given this data, we're actually going to try to provide a function that depends on this data. I'm really going to use an n here, or maybe a little hat to denote quantity that depend on the data. Typically, we'll denote these old guys. S is what you call the training set, is what you're given today, and your goal is to do well on future data. All right, and this is just a simplistic picture. For a bunch of reasons. First of all, I'm putting here 4 points. Okay, there are many applications still now where the number of points is not that large, but there are applications when the number of points is 10 millions or more. Okay, so that's one first thing to keep in mind. This picture is misleading because I n points where n is 4, whereas n can be order of hundreds, thousands, millions, or more. The other thing which is misleading is that I put the input dimension to be just one number, whereas it's actually kind of hard to find an application where you actually only have one number describing your inputs. You can think of any application you want, and typically the number of inputs gets quite large. Say one running example that we probably can keep in mind for the rest of the semester is the case where you have images and you want to make statements about images. Say, for example, what is in an image? Or images of object and you want to say object is in an image. And then typically, the more simple things you can do is just assume that each image is described by the value of its pixels. And you immediately see that even in this case, you go up to an order of tens or hundreds numbers to describe each image. And it's not uncommon to find application where the number of numbers that describe the image might be order of thousands or even millions, okay? Because in some sense, it's up to you how many parameters you want to put in there. So these are two things to keep in mind. We often deal with massive data set. Big data set became a trendy word a few years ago. And we're also dealing with high-dimensional phenomena. We are dealing with high-dimensional problems. The number of variables can be exceedingly large, okay? Aside from this couple of comments, this problem is, calling this problem just learning is perhaps a bit of a stretch, because at this level of generality, you find this same problem in what people call approximation theory, in sampling theory, in classical statistics, and so on and so forth. We can make perhaps another example, which it starts to be slightly more interesting, still simplistic, and it's the case where we have a bunch of points. And we want to classify them in class 1 or class -1, okay? So don't be misled. This is not x and y. This is just x, okay? This is the space x, which is made of now 2 coordinates rather than 1. Where is y? Y would be somewhere here, okay? And we want to find the function as what? Well, if you look at the level set 0, where this function changes sign, you should get another line that ideally, put the crosses on one side and the circles on the other side. This is the classical problem of binary classification, okay? And the basic idea of having images of cats and dogs or whatever you want, and you want to discriminate between them is an example of this. Again, the idea is that this is the case where the images are just 2 pixels, which is not very interesting in practice, but this is what our intuition can do. All right, so this is just the basic idea. What we need to do is to actually get a mathematical formulation out of this. And one thing we're going to try to do is make always clear what we mean by a problem and an algorithm to solve a problem. Okay, we're hardly ever going to start from the algorithm. And we're also going to try to make a distinction between statistical algorithm, which are effectively abstract procedures that might not be directly implementable in a computer, and actual algorithm, numerical algorithm, that you can implement in a computer. Okay? This distinction will be clear, but at this level of generality, just think of the idea that you have statistical requirements and computational requirements. And when we think of an algorithm, we want to keep an eye on both things. Now, one of the nice things about supervised learning is that it's one of those problems where we are at a good level of understanding of the problem. And the nice thing is that the problem itself is defined by 2 ingredients and can be defined by 3 lines. The ingredients of the learning problem are 2. The first one is the probability space. So we take the pairs of input and outputs, and we just think that they live in some space, okay? X and Y. I'm gonna, for 3 lines, it's so short that for 3 lines, I'm not gonna comment too much on it. We're gonna spend the rest of the class doing it, okay? So for now, there is a probability space and a probability distribution in the cross space, okay? That's ingredient 1. In most of what we do, we will not try to estimate the probability distribution, but just a function, as you see there. And so we will need to measure error, and that's the second ingredient of the game. Function that goes from the output space to the output space and the output space to the real line, okay? It's what we call the loss function. It takes pairs of outputs and returns a real number, which is positive. You can think of it as a cost, okay? And typically, from a technical point of view, we're going to assume that this loss function has some nice integrability property with respect to the entries. We're going to comment on it in a minute. Given these two ingredients, we're actually going to define the problem as the following. Solve a minimization problem of a certain quantity, which we're going to call the expected loss or the expected risk. So this is the integral of the loss function with respect to the distribution. If you are allergic to integrals, but you're okay with the random variables, this is the expectation of the loss with respect to the pairs x and y, okay? And our goal is to estimate minimize this, because the semantic of this object is that we want to make the error on any possible pairs of points small. So this is exactly what we would like to do, okay? The caveat is that we don't actually have access to rho. Rho is fixed but unknown, and all we have is that we have the training set, okay, written over there. We assume to be sampled to the product of n times rho. Rho is fixed but unknown. Okay? So the whole game is essentially, this one line is the one for which we call this thing learning. The notation is condensed, okay? The nice thing is that it's just three, this is the whole thing, okay? This is the problem we're going to discuss for 15 lectures or more. The notation still has a lot of interesting stuff happening. One thing is this little symbol here. It says that each pair comes from rho. And we're just taking the product distribution. Do you remember the product distribution where things are independent? Okay, so we're assuming that the samples are always coming from the same distribution and they're all independent to each other. Most importantly, we assume that it's fixed, but it's not known. So all you're given to solve this problem is actually these n pairs. Now you see immediately how we somewhat incorporated, try to encode that is a notion of today and tomorrow, of predictivity, of generalization in the definition of the problem. The problem would be to do well tomorrow, to do well on future data, but all we are stuck with is what we have today. We also see that there is no way to solve this problem perfectly. Okay, in general, it sounds very unlikely. We will have to settle for an approximate solution. When we measure the quality of a solution, we will not be able to say, oh, this is a perfect solution of this. We'll have to say this is, there is some level of precision in which we can solve the problem and make sense of what does it mean to be precise. Everything is stochastic. We're looking at functions and so on and so forth. Okay? This is it. Okay? This is the whole problem. Yes? Down here? So I'm being a bit vague here. These are all the functions from the input to the output. Okay? That clearly doesn't make too much sense. It's almost correct, though. So what do you need? You need essentially, when you do an expectation of a random variable, you have to be sure that the expectation is well defined. So strictly speaking, you have that thing to be a random variable. So if you look at the Wikipedia entry, it says that this function and this needs to be measurables. Okay? And that's all you need. So this space is actually not the space of all possible functions in the world, but the measurable function. But if you're human beings, usually, and you're not studying too much math in your life, you don't worry about measurability too much. So that's all, it's there. P rho xy. So this is just the integral with respect to the distribution. I'm going to comment, if you're used to the notation pxy dx dy, that's the same thing. We're going to comment on why I use this notation. This is the usual integral with respect to a distribution, okay? I'll remark in a minute. I'm going to use this notation throughout the course, and I'm going to remark in a minute why. So, no, one more.
What's the last word at the bottom statement? Sorry.
Rho is fixed but unknown. That's good. No, this is, you know. Anything else?
What's the superscript of row on the bottom left of the board?
N, row N. Taking the product measure. You know, I have a probability distribution, then I take a sample from the same distribution twice. So the distribution of the pairs is the same distribution to the square, to the third, to the fourth. Okay? So the question was, what is this guy? And I'm just telling you, what is this guy's N and why is there? Is because I'm assuming everything to be independent. Okay? What do we want to do next? We want to try to keep this guy there and just explode these 4 lines in discussing them for 50 minutes, okay? So we begin basically listing, you know, let's list all the ingredients, okay? The ingredients are data, space, the data distribution, so XY, the data distribution row, then the loss function, the expected risk, so this is L, well, I guess the idea that we have to settle for an approximate question mark, what the hell do I mean by that, right? These are the main ingredients. Okay, so let's zoom in and take a look, okay? So the data space. We call the product of these two things the data space. And notice the is very democratic. We think in our head as X is the input and Y is the input, but so far, you know, I can switch order, you know, doesn't really matter. The kind of thing that distinguish the classical, let's make example now. For now, they're just abstract stuff. Let's make example. What is the first example that comes to your mind of an input space X? This is the part when you say something. What? Real numbers, okay? R. Or fancier, but not too fancier than this. Real numbers to the D. Okay? Oh, let's be fancier. What are pixels? List of numbers. Let's give mathematical examples. Functions. Okay? This stuff can be, you can think of X as a function from some domains to the real. Enough math that for you, when you see an image, is a function from R2 to R, okay, rather than a collection of pixels. Fair enough. There are actually a lot of cases where this makes sense. What else?
So yeah, 0, 1 to the n.
Zero, one, as in bracket. This? Yeah, this is already nicer, right? It's kind of a nicer. I mean, it did start to be a bit. Okay, now I'll keep on going for you. What about the space of input is a space of, well, this is the space of, essentially space of strings. What if the space of input is a space of vectors, but where I make all the entries sum up to 1. So it's effectively a space of probability distribution, okay? I don't remember, what is the notation for this? Let's write something like this. The simplex. These are all vectors that sum up to 1. So I can interpret the entry of the vector as probability masses, okay? But actually, you can actually go continuous. You just assume that the inputs are actually distributions, okay? Distribution over something. It's a special case of functions, but it's the case of function with some properties. And what if the inputs are actually graphs? Each input is a graph, and I have to distinguish between different kinds of graphs, the good graphs and the bad graphs. Okay? And again, I'm not going to give you a ton of examples here because this is not what this is about, but you can just imagine that there are tons of situations where you can fit any of this. And you can keep on going. Okay? You can take space of matrices. The input are a space of matrices, is a space of matrices. Okay? In this mess of example, there is one distinction that actually makes sense to make, which is all these examples and many more, and all these examples and many more has one fundamental difference. What is it? Yeah, but not really, right? Because, for example, he's saying countable, like, if you have discretely many, things or continuous, but not really, because this guy and this guy are essentially the same. I really want to make the difference what's happening here and what's happening here. What? Bounded? No, not really. I can bound or not. Measurable? I don't know. That's complicated. A what?
The bottom one seems to be processed.
Right. I'm looking for one very basic mathematical properties.
Whether we have it or not, it's not to say which one is larger or which one is smaller.
Yeah, but that's specific for this guy. I actually want something that is specific for all this guy at once. And again, I can put matrices and other stuff and all this guy at once. And the property I'm looking for is it's a vector space. Okay. If you take, what do I mean by that? We don't mean vector as in vectors with a bunch of numbers and it's an arrow with a thing, but we think in terms of linear spaces. If you take any of these two guys and you sum them up, you get still one of these guys. And if you multiply by a number, you get one of those guys. Okay? This is the structure of linear spaces. Okay? This is one of the ingredients that makes your life nice. The fact that we know what linear spaces are. They're simple, they're nice. We're going to put some more structure on it. Vectors is what we know how to handle and what we think about for 90% of our time. This doesn't have a linear structure. Okay? By linear structure, it actually means the story that you can sum two things up or multiply by a number. If you take any of these two guys and you sum up and you sum just in the trivial way, you don't get the string again. If you take any two probability distribution, you just sum them up, ignoring that they're probability distribution, you don't get the probability distribution. You have to renormalize. Well, of course you can do it, but then it's not just a linear space. Same thing if you multiply by numbers. Take a graph. You don't even know how to sum up. It's not an obvious thing how to sum up a graph. Okay? Their example here, even matrices and so on, keep on going. Okay? So to some extent, there is this big distinction between spaces that are linear, because they already give us, we already know a lot of things that we can do, and spaces that are not linear. This is not the only property that is useful to have in practice, but these make a big distinction. Okay? Yeah, we're going to discuss about that. He's talking about more properties, okay? He was basically commenting using words that we don't want to use for now on the fact that, linear space is one thing. You can have more stuff. For example, strings, we don't know how to sum them up, but we have a bunch of ways to measure how distant are those strings, okay? If you know nothing about this, there's nothing you can do, okay? The funny thing is that, let me say, just to add two comments before going back to what you're saying. I'm not going to repeat this, but I can do the same distinction for Y's. Okay, give me an example of Y's of spaces of outputs are kind of the same. Okay, kind of the same. The interesting thing is that whatever is below, whatever is more messy, we actually call structure problem. Okay. So ironically enough, the spaces with lack structure, for example, the linear structure, is what typically in the literature is called structured problem, structured in the input or structured in the output. So if you hear about structure prediction, it's typically about solving problem where it's either the input or the output doesn't have much structure, in fact. But they have some structure. So they are not linear spaces, but as he's saying, you have to have something, okay? For example, you have two ways to measure how distant are two things. That's the very basic property. That is what is called the metric property, okay, having a distance. So this is one first, taxonomy in this world. We have an input space, we have an output space. The typical distinction which we want to do is, do we have a linear structure or not? You will see that once you have a linear structure, immediately you know how to do a bunch of things. When you don't have it, you have to think more, okay? Another interesting thing is that for the input space, we all give having a different input space is not enough to give the problem different name. Having a different output space, interesting enough, it is. Okay? So we can actually give names. For example, if you just assume this to be R, what is the name of this? How do we call a learning problem where the output is R? Regression. What if it's RD? Well, it's multivariate regression. What if the output space is a function? Well, we actually call it functional regression. And we keep on going. Okay, we got different names. What about here? Well, if the output is just 0, 1, or plus minus 1 is the usual convention, we call this binary classification. If the output is a list of numbers, or symbols for what matters, from 1 to t, we call this multi-category classification. And if you actually take subsets of this, so this is the case where inputs can be of either one of two kinds. This is the case where they can be one out of t cases. You can actually assume that each input can actually belong to simultaneously more than one of these. For example, you have an image that contains a cat and a dog, but not me. Okay? So it means that I'm going to assign two labels to that guy. And that's the case where I'm basically taking subsets of this. Okay? The one that I have and the one that I don't have. And you can keep on going. Okay? We didn't learn much so far. We just learned that there is this one distinction that you might want to keep in mind, that there are a bunch of different problems, and you see how things can be general, okay? We're going to try to make somewhat the point when X is just a vector space and we want to, and when it's not, because you see that the list is long. I mean, X is, this guy, which is what we typically like to think about, is actually just one of many, many examples, okay? And we discovered that besides this distinction, when you make, depending on the kind of structure you have on the output, typically you give a different name to the learning problem, okay? Slightly different name. Still supervised, still a loss, blah, 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 but you give a different name. All right? Far so good? Ingredient number 2, the distribution. Now, the distribution is this guy. And we basically just need one basic assumption, which we almost always give for granted, but it actually, in this level of full crazy generality, it is an assumption. And it is the fact that we can decompose this distribution in a marginal and a conditional distribution. It takes a while to find cases where, this is not true, but we're going to only assume it's true. This breaks the symmetry between x and y, and now, somewhat point us in the direction of seeing as x as the input and y as the output, because I'm conditioned in this way. And the idea here is that now, given an input, I want to predict an output, but also this starts to tell me a bunch of things. The relation between input and output is intrinsically not deterministic in general. Given an input, I'm actually having a whole distribution of possible values. So you can interpret this in a bunch of ways. For example, you would like to think of this as some kind of noise, okay? I would like to say what is the output of this x. I'm given this x, I give it this image, I would like to know if it's a cat or a dog, but actually with a certain probability, I'm going to say something different, okay? Or I have a certain distribution of values, say for the temperature or something, and I would like to say exactly what is the temperature tomorrow, but there is some noise and I'm going to have some perturbation. This is somewhat the intuition behind this kind of stuff, but a lot of stuff can go in there, right? You can have a picture of me and George, or maybe somebody that looks a bit more like me, and we look alike, okay? So we start to have a whole situation where we have distribution of things that are similar, and this is encoded in this, the fact that two people can look alike is encoded in there. And maybe the fact that you have a certain amount of resolution in the way you encode images. So if you blur an image enough, you can confuse me for somebody else. It's all in there. We basically dump a lot of that we have about the problem in the fact that we assume that the data are probabilistic. There are a couple of examples for the conditional distribution that you might want to keep in mind. Because essentially in that list of problem in the linear case, a regression, and problem 1 in the nonlinear case are the most studied one, and the rest we're trying to figure them out, okay? And in these two cases, there are two classical special examples of this. The first one is regression. So you actually assume that there is some special function that you call exp. This is a function from the input to the output, and let's just assume that the output are the reals now. And then you define, so you're given a function f star from x to y. You're given a random variable, which is, let's say, normal Gaussian. And then what you do is that you have an input point. Okay, you sample an input point according to some distribution. We're going to discuss that in a minute. Then you sample one of these variables. You evaluate the function at that point, and you add this. Okay. All you are given in the end is this guy and this guy. But this is one way to define a probability distribution on the output. What is the probability distribution on the output? Well, the noise is a standard Gaussian. What am I doing? I'm just recentering the Gaussian. Okay, so this guy is still a standard Gaussian, but rather than being centered in 0, is now centered where? F star xi. And the noise is sigma. Okay? No, you can do it. You can be fancier than that, but let's just assume it's fixed. This is just an illustrative example, and the meaning is not to be fancy or anything. It's just to say, see, in this one example, I really make sense of the fact that I want to think of rho as somewhat described, the rho y given x, the condition is connected to the noise, because in this one case, it is exactly the noise. You know, if you think of it as the noise, which is what, again, if you're not from Mars, you do, then this is exactly what's going on. The noise defines the distribution. I would like the noise to be 0 and just have a deterministic thing, but I actually add some perturbation. Now I change my function. Okay? So this is the classical regression model, and this is why you can think of that as a noise in certain situation, or induced by the noise in certain situation. Okay? So this is regression. If you consider classification, when I say classification without saying anything else, I always mean binary classification. Then the situation is something like this doesn't really make sense, or it's not obvious at first sight. What is a good F star for classification? It's not clear. I don't even think in terms of F. I only think in terms of the decision boundary or something. So one thing to notice is that typically what you have is that the rho of y given x is given by what? Well, if you're in binary classification, you have two choices. So you can think in terms of a full distribution, but you just 2-point masses. You have rho of 1 given x or rho of -1 given x. Okay? And that's all you have. You have the probability distribution of class 1, the probability distribution of class -1. And here it's not completely obvious, you know, how to think of this as somewhat measuring the noise of the problem. Okay, and in fact, you know, this standard way of thinking about noise doesn't quite hold anymore. Yep. I don't.
So one is of the plus, and x is of the plus.
Yeah. So this is just classification, which is binary classification, which is the case where the output is either 1 or -1. Okay, you have images of cats and dogs. Okay, cats or dogs. This is the probability of that an image is a cat, or a probability that an image is a dog. Okay. And what I'm trying to say is that, you know, just ponder for 1 second that, you know, how to think about this as noise is not completely obvious. Okay. So, you know, a mental picture you might want to have, I'm going 1D rather than 2D, is that, you know, this is the distribution of class 1 and this is the distribution of class -1. And something like how much these classes overlap can be seen as some notion of noise. And indeed, this can be formalized. And when you try to make things quantitative, quantity like this start to play a role. But we're not going to do it now. We're not going to really need this. But this is just to tell you, clearly this tells me how much things get blurred out in the output space. I can think of it as a noise, or more generally as some notion of uncertainty I want to attach to my problem. Okay? I'm going a bit fast because I'm reviewing things, which, again, I'm assuming things. I'm just going to add a few cherries here and there for you, but not any substantial new thing. Okay? It's slightly more interesting to think a bit in terms of the marginal distribution. So why do we actually need to talk about the marginal distribution? Okay, actually, if you look at a lot of statistics, it's often assumed what is called the fixed design setting, where the inputs are assumed to be fixed once and for all. This is an heritage of the fact that mathematically this is nice to study. So if you want to prove stuff, this makes your life easier. But also on the fact that, especially in low-dimensional scenario, it was sometimes possible to actually pick the point of the input. Suppose that, you know, you really have a problem like this. 1D, you actually might be able to pick the points as you like. For example, regular on a grid that is of equispaced point. Or you might decide that there are certain regions of the space you want to sample more or less. But imagine that you're in a situation that's not up to you, okay? The sampling is actually something that you can control. For example, you can have sample with noise. So I would say, oh, give me the function here. And you're like, I give it to you here. About here, boom, same, okay? Or rather than noise, there are really constraints in the sampling world for which certain things are more likely to be sampled than some other, or there is some more noise in some region than some others, okay? You have to account for this. And then one way to account for this is basically assuming that you have a distribution over the inputs, okay? And you're gonna sample your inputs according to this one distribution, okay? Again, one could be more specific than this and try to make use of the extra assumption you can make. For example, you can say, I have really this model of sampling is something plus some noise. This is fairly general. It's like that. It's like that stuff that I deleted, that I threw up. This is more, this symbol is more general than any of these two examples. And same thing happens for the marginal distribution. The marginal distribution typically account for our capability of sampling more or less well the input space. Now, an interesting observation comes from the idea that, let's just consider the case where x is r to the d. As we said before, typically we have in mind situation where d, when you have vectors, d can be very, very big, okay? So say t is 10 to the 5, all right? Now, a recurrent theme of this course will be that if you're having this very high dimension, if you don't have much structure, it's unlikely that you will be able to get anything out of your data, okay? If the data are really high dimensional, okay, in a lot of situations it will be impossible to get anything out of this. But in most situations, there is actually a lot of structure, and a lot of structure is what allows you to get something useful out of your data. Now, in the case, rho x is the first step, allows us to somewhat take a first peek into this. What is the idea? Well, if we just assume that the input is one-dimensional, okay, if I have to draw a distribution, I'm just going to say, look, yes, this is the true function, okay, let's say the regression example, but I have bad luck, and, I'm not able to sample everything in the same way. So this is x, this is y, and say, this is my distribution over the x's. It's just an example. I'm not sure it makes too much sense, but what it means is just, I'm more likely to sample, the point in the middle than the point in the outskirt. And just notice that already this means that, the samples are going to look like this. Okay, now this is actually the only one case. Let me just, function look like this, okay? So you yeah, no, that's fine. So suppose that your distribution is uniform. Roughly speaking, you get a sense of this curve, is how that give you 10 points, roughly speaking. If instead you sample this way, how is the sample going to look like? Well, you're going to have a bunch here, and then here you have almost nothing, okay? So you might have a situation where you just have 1 point here and nothing there, or maybe 1 point here and nothing there. So you may actually this bump going up, because you don't see, in some sense, this distribution doesn't suggest there is much going on in there. And this is just to point out that even if you had no noise, okay, in the output, just the sampling in the input is an annoying thing you have to be worried about, okay? Especially because this is very simplistic. This is just the one dimension, but you're actually going to look at situation where it is 10 to the 5, okay? And this points us to another thing that might happen. If you're in 2 dimensions, say, now let me just forget about the output and let's just look at 2 dimensions. How would a distribution look like? Well, God knows, it's complicated, but let's just make one observation. So if you, for example, take a picture of images, say, this is my face, and you suppose that you're going to plot it in the high dimensional space, how is it going to look like? A mess. But if you take any image, say, I take pictures that are 20 by 20, okay, very small, 400 dimensionals. Now take any 400 dimensional vector. Is it going to be a face of mine? Of course not, okay? So if you go in this dimensional space, which is 400 dimensional, my faces are going to occupy some region of this space. It's not the whole thing, okay? And this region is going to have some structure, because whatever you find here, you're going to find very similarly here. My face has a certain, I'm just saying frontal faces with no background. There's a lot of symmetry in my face, and probably this suggests that my face is going to have kind of lower dimensional structure, okay? Not everything is independent to everything else. The simplest way to abstract this idea is to basically assume that this thing here is actually 400 dimensional. Okay, it's not 2, it's 400 dimensional, and my faces has to lie in some subregion. Now, if I assume that it's a subregion and everything is independent, it will be a blob inside of this bigger world. But if I actually assume that things are correlated enough, are dependent enough, it means that whenever you know what's happening here, you know what's happening here, which actually means that you have 1 dimension less. Okay, in 1 dimension, in 2 dimensional you have 2. So I have to kill and assume that they're dependent to each other. Okay, so instead of a blob, I actually have a line. I have to go down 1 dimension. Okay, because things are dependent to each other. I just have this complicated line. What is the marginal distribution? Well, it's a distribution over the line, okay? Over this line here. Just to catch up in my little drawing, this is just the input space, which is clearly R2, but you can think of this as 10 to the 5 instead. Okay. This is the set where the distribution is supported. Okay, is what you call the support of the distribution rho x, which is contained in Rd, but is a smaller set. And so first thing that you want to think about is the fact that when you write rho x, you're not just writing something that has to live in the full dimensional space, or rather it has to live there, but it might occupy just a smaller region, okay? And the simplest mathematical object that describes that region is typically thinking of a surface, or a manifold, if you want to be more general, okay? So when we think of rho x is where somewhat the structure of the input is encoded. And the fact that we don't use the notation of, the notation px dx to write rho x, we're going to use this notation rather than this, is because when things are in like this situation, when things are like, when you have a distribution that sees the whole input space, doesn't really matter. Typically, this is an innocuous change of notation. When you're in this situation, for example, you have data that are supported on a circle, and you have to look at the density of the distribution over R2, that requires some thought. Because if you remember, the volume of a line in R2 is 0. Okay? So if you look at the density, which is the volume, the local volume of this line, doesn't really make sense. So the notion of we don't want to go into detail of that, but if you play this game of assuming that thing can be high dimensional but lie in a lower dimensional space, the notation that you typically are used to, the one about density, requires some thought. And so rather than actually entering the detail of the thought, we're just going to use this notation. Sorry, there should be a d here. Okay? So when I write that integral, instead of writing px y dx dy, I write this. Why do I do it? Well, because you can think and remember in your head that sometimes things lie on lower dimensional structure, and that's where this notation is correct, and this might be correct or not, and you have to pay some attention. So it's just a reminder for you, and it's not too much different, so you can deal with it. Okay? Which one?
Something about the marginal.
Yeah, because this is the support of the marginal. And the marginal is actually, so in this case, this is the support of the marginal, and the marginal tell you which region have more mass than others. Here, the support is this line, literally just the line, and the marginal tells you in which region of this line, just this line, you have to put more mass. So if I venture into trying to draw it, it would be maybe something like this, something that says that this region of this whole curve has more mass than the rest of the region, just in the input space, no output in this game. Make sense? Okay, so we're going slowly here. We just introduced the input space, the data output space, and the probability distribution. We discovered that we can split it in input and output, and there are a bunch of situations where you can think of these different cases. For the output, classification and regression are the two main examples, and for the input, the marginal distribution is a reminder of the potential structure in these high-dimensional spaces. Okay? So what do we want to do? Well, any questions about this stuff so far?
So at what point do you draw the line between just assigning and low probability and taking it out of the support altogether?
Say again?
So at what point do you draw the line between excluding it from the support?
Yeah.
And just
So this is so what the question is about. Here I'm just saying, oh, you have a lower dimensional thing, there is a support and it's not the whole thing. But in practice, they're not going to have this, okay? Even my faces are not the whole thing. Maybe because if I have some noise, if I touch pixels, if I have pixel and I touch noise, and noise is pretty wild, you're actually going to have my face all over the place. They're going to be mostly around something small, but there's going to be stuff all over the place. And his question is actually taking a step further and is like, okay, where do you say what's the actual support and what is the rest? And I don't know. Okay. The point of this is just to make you think of the fact that this is the most simplistic situation. I'm just telling you. Suppose that there is a clear cut that typically there's not between what's in my face and what's not. In practice, this is just a vast simplification. You're going to have to be fancier than that. And you're going to take, say, a distribution, which is a convolution of two distributions, or a sum of two random variables. One is my face and one is noise. And then you have to figure out what's going on. But at this level, again, at this level of generality, is just pointing you the direction of the fact that there is such a structure. Asking, answering the question of what does it mean to be exactly supported or not is basically the problem of what is called anomaly detection, okay, or support estimation. And it is a learning problem in its own right, and we're not going to discuss this. Okay, so this is just not meant to answer a fancy question like yours. It's just to tell you to think, if you have not done before, which clearly you probably have, to think about the fact that this row of X lives in a large space, but I actually describe only a portion of it. Okay? Other questions? So what we want to do next is getting closer to the actual problem. And the main point we want to make is that, see, everything so far is probabilistic, and we actually describe to allow ourselves a probabilistic framework to basically encompass different notions of uncertainty, sampling, noise, similarity, quantization, and whatnot. Yet, from line 1, our goal is declared to be not to estimate a probability distribution, but just to be able to make statement about an input. Okay? So we actually just want a functional relationship. So given an input, we're actually going to spit out an answer. Okay? While it's written here that there is no such a thing as an answer. Okay? There are many answers. Some are more likely than some others. So we're going to make mistakes. Okay? We have to make mistakes because we stick to a deterministic functional relation or a fixed functional relation, whereas our output is actually probabilistic. So that's the reason why we need to introduce the second ingredient, which is the loss function. The loss function is the simplest of the thing we can do, which is basically saying, look, if you tell me f of x, and then I reveal to you y, the loss function tells you the price you pay by saying fx when you should have to really say y. Okay? Is a point-wise measure of the error. It doesn't tell you what is going on ever. It just tells you for every decision you make, the price you're going to pay. Okay? Let's make example. It turns out that, again, the standard case is the case of regression, where the loss function are typically have a special form. I'm just going to... loss functions are typically symmetric. It doesn't really matter if you put f of x before or after y. And so let me just use the notation y prime. Remember, the loss function is a combination of any two outputs. Okay, so I'm just write it like this because I don't want to keep on writing f of x for 10 minutes now. In regression, it turns out that loss functions are typically not any function, but they always depend on the difference between these two. Okay, between the difference between the two outputs. Example, I guess the most famous one is the square, the v to be the square, so you take y minus y prime square. Another example. I mean, it's obvious why you want to keep the square, right? There is no particular reason to prefer one side or the other. you took the square. Actually, if you ask anybody to give the first example, this is not the first. This is the first after you realize that whenever you have to take a derivative, it's good to have a square. But before realizing that, what do you say? You just take the absolute value. Then you discover that absolute value is annoying because it has a kink, and then you have to worry a bit about it. And these are the two main examples, the square loss, the least square loss, and the absolute value loss. There is another loss which is somewhat, I don't know if it's useless that much, but is the one that was often mentioned in statistical learning courses, which is what is called the the epsilon insensitive loss function. Well, let's draw it because then it's obvious why you call it like that. So here I can just write y minus y prime. This will be the square loss. This only straight will be the absolute value loss. The epsilon insensitive loss is, it looks like the absolute value, but not around the origin. So it's flat around the origin. Minus epsilon, epsilon, and then it goes up. Okay? So written like this, and it's the maximum between y minus y prime absolute values minus epsilon. 0. And unlike the other loss function, this one loss function depends on a parameter, okay? So it really opens up questions about how you pick that parameter. But the basic intuition is when things are really small, I want to be robust because I don't know what's going on. So I'm going to set them all equal to 0. If things are big enough, I'm happy. So in that sense, these two losses are more robust than this one. This one starts to pay a lot and keep on going. This guy tries to pay as little as possible while they can. And clearly here, the slope doesn't really matter. It's the shape what makes the difference here. Okay? All right, classification. So also in classification, you can write this as a function of one variable. V is a function of one variable in that case. It only depends on what is the relevant quantity here in classification, binary classification. Not the difference, not that obvious. The product. Okay, why? Because you take two things. If the product is the same, is positive, it means that they're either both negative or both positive, but the same class. When they are not agreeing, it means that it becomes okay. So something like this, and people often put a minus there just for the sake of it. Okay. So what is the most common example? What is the obvious way to measure error in classification? If you get correct, you count hinge loss. If you get correct, hinge loss. No, you count? This afternoon, we have to design a system, and we decide, okay, if you make a 0, you count 0. And if you make a mistake, you count 1. Why? Well, because you can always think of another number, but 1 is good enough. Okay. So this loss function looks exactly like this. If this is the step function, okay, you can simply write it like this. And this is, if you want, you can also write it the indicator of when y is different from y prime, okay? Let me draw it here. Put y prime here. This basically says when this thing is, I put a minus here just because this is the way this theta is typically defined. This is the so-called heaviside step function is defined this way. So when I have something negative, I put 1, and when something is positive, I count 0. Okay. This is, I guess, to some extent, the most natural choice of a loss function for classification. Just say I pay nothing or I pay some, and some I decide to be 1. Clearly, it doesn't matter if you put 15 or 3. Okay. From a mathematical point of view, here we saw that the square loss is nice because you can take derivatives easily because it's continuous and differentiable. The absolute value is continuous, but it has a kink in the middle, like that. This one is actually worse than that because it has kinks, but it's also what? Magic word here is not. The problem is that it's not. But also that guy is not differentiable, so now we make it apart. So this is not differentiable again, no? Convex. These guys are convex. These guys are not convex. And no, non-convex stuff fashionable this day, but still you might want to stay away from it whenever you can, because it's immediately a mess. And this guy is definitely a mess. It's a step function. Try to differentiate this guy and set the gradient equal to 0 and get anything like, finding a minimizer. You typically get hardness on your head in a minute because it becomes combinatorial immediately. You have to try your blah, blah, okay? So this guy is beautiful from the information theoretic, from a learning point of view, is the right choice, but he's also the one that you want to try to stay away from as much as you can, okay? So what you typically do, you try to keep everything you like and kill the one thing that you don't like, which is the lack of convexity. So our friend actually said for the first thing, hinge loss, which is actually that one choice, okay? It's the choice where you basically say, I like to be 0 there, but also I try to make this thing convex, or smilish, okay? Now, the problem is that I want to be flat, and I don't want to bend this much. At some point, I have to pay in the positive line, okay? So here you typically decide to pay already at 1, okay? Here you don't pay. Here you already start to pay, even if you're on the correct side, because you want to pull that thing up. And then you just go linearly, okay? This is what is called the hinge loss. 1 minus y prime plus, which just basically means that you take 1 minus y prime or 0, the maximum of these two, okay? So basically, look at the product, but don't compare it to 0, compare it to 1, okay? So if you're smaller than 1, okay, you start paying. If you're bigger than 1, so it's a bit of what, a word that people like to call, using this thing, is a bit of a margin, okay? There is a region around the 0. It is in spirit similar to this. There is a region around 0 where you don't want to pay, okay? And here you're basically saying, well, I'm going to start paying something around there, okay? Now, this one is convex, okay? It is non-differentiable, okay? Suppose that you want to try to make it differentiable, okay? You have to change it. How would you change it? You can do a couple of things. One is to just take this kink and like massage it. That's one thing you can do. Or you can actually give up this thing being 0 exactly, and you can try to get something that looks similar, more like this. And this is what people call logistic loss function. Okay? It turns out that this expression is exactly something that looks like this. The log and the e somewhat counterbalance the effect, so there is no super slow or super fast stuff. You basically have something basically linear here and something basically linear there, and then this transient around 0. Okay? So it is the hinge loss, this is the logistic regression loss. I actually would like to put back the square loss into the game. It's my favorite loss. So first of all, the usual check whether somebody already seen this before. Do you see why this can be written in that way, just as a product of two things rather than the difference? In classification, not in general. It turns out that the square loss can also be written this way, and it just become 1 minus y prime squared, okay? That's the same, okay? So while you think about why it's true, I'm going to draw it. It means that I basically pinpoint things at 1 again. Then I have something which sounds a bit funny from this plot, okay? Because look, this is a parabola that passed through 1 and then it goes up. So it kind of makes sense from the discussion we've been having so far. It kind of makes sense here. It's a bit steep. You start to pay a lot quite soon. But here it looks weird because it actually looks like you're actually paying a lot, even if you're correct. This picture is somewhat misleading. There are actually many other reasons to see that this is actually a fine guy, okay? He's just shooting for more. It turns out he's shooting for more than just the correct classification. So keep that in mind that this is my favorite loss. This is very important to everybody. And also that there are other reasons for which we'll hopefully convince ourselves that this is a fine loss for classification. Do you see why I can do this? Y here is just a plus or minus, so I can just factorize it out. Okay, there are a million ways of doing this, but one way is just take this y, factorize it out, is y squared, so it's 1 or minus 1 becomes 1. And then you get the 1 over y here, but 1 over y and y are the same because it's just plus or minus 1. My Italian hand-waving proof, but it's one line, so we don't want to write it down. Okay, so these are the most standard examples, and they're actually kind of useful because if you get out of this world, get out of the world of regression and classification, I listed 3 gazillions examples of input space, okay? Well, good luck giving, the standard loss function for any of this. This is actually a matter of research, okay? If I give you a space which is a space of functions, well, you can generalize some of this. It's not obvious. And especially if you go to, say, multi-class classification, multi-label classification, a structure prediction of other kinds, big part of the business is what is the loss function you want to try to minimize, okay? So while the loss function is the key ingredient, and is the key ingredient that we seem to be given, okay, is the one that defines the problem, the exact nature of what is the right loss function is something debatable, okay? And here I just show you some example, although I'm not even telling you which one you should use, which is already a first question. And more generally, I'm also telling you that if the output is more complicated, I'm not even giving you examples at all. Okay, so I'm more suggesting that the matter becomes complicated when you go to more complicated domains.
Is that an excessive?
Right. So this points to a little subtlety. So the question is whether why. So if I put a sign or not here, should I put the sign or not? Well, so there is a little subtlety here. That, I'm not sure what is the best way to resolve it, but let's discuss it 3 seconds. You see the way I defined it? It's actually a loss between y and y. So if these are real, if it's regression, it's 2 real numbers. If it's classification, it's 2 binary numbers. Okay? So it's 0, 1, or minus 1, 1, and minus 1, 1. Okay? So I set up the thing so that this thing is always just binary. He's asking that because when you actually, in practice, one of these 2 guys is going to be a function, and typically your functions are actually real valued, even in classification. You're not able to minimize Boolean functions. We don't handle Boolean functions well. So actually, typically one of these 2 guys is going to be a real number, and one of them is going to be a binary function, and we'll discuss in a minute why typically you take the sign of the real function. So in regression, you just take them, they're both real numbers, and you're good. In classification, if I actually say that this guy is f of x, then we have to discuss a bit what it means, okay? And typically in practice, you take the sign. The product it still works fine. That's why we write the whole real line, okay? We already had in mind the situation in one of the 2 can actually span the whole real line, okay? But these are somewhat important subtlety, but I wouldn't indulge too much into these right now, okay? Does it make sense? Good. So you would have to change the problem in line 1, right? So right now we're just doing this. So what he's asking is, can I put an assumption here that things are probabilistic? Yes, in some sense you would have to take some kind of a generative point of view. So the idea is that you would have to take a function f that is now not just a function, but is actually a function of some parameter, or was a process, okay? And then you would have to define the problem so that you have to account for that. How do you want to treat the probabilistic aspect of your function? So typically from a Bayesian point of view, one can do that. He assumes that the function f is itself a random variable, and then an extra expectation can be put there, or some fancier notion of, that controls the probability there. You can do that. We're not going to do it at all, ever, just because it makes stuff more complicated. Okay? All right, so okay, so now we can keep on going because now we're almost done. So now we can define, the problem is define one basic guy, which is this guy called the expected risk or expected loss or expected error, which is this quantity here. Okay? So literally basically says, I have this measure of error that I picked, is one of those. And now what I want to do is that I want to sum the errors over all possible pairs but I want to do a weighted sum where things that are most likely to be sampled should count more. Okay? That's the usual meaning of an expectation. And this, again, from a semantic perspective, you can think of this as something that encodes both the past and the future, what I have today and what I don't have. Is the full population. That's one word that is often used. Where is this defined? Well, it is defined, again, you need to be sure that this guy is well defined. And typically, we're going to define this over all the function from x to y. Well, let me write immediately r, where is measurable. And whenever you see measurability, you might want to go back and look at it, but it's basically the one property that makes sense of that integral. Okay, ensure that that integral is well defined. This thing is also sometimes called the risk. Okay, sometimes called the expected risk, and the reason is because in classification, when you assume that the output is just +1 or -1, then E of f you can check that is also the probability of the x and y such that f of x, y is smaller than 0. Okay, so if you take classification and L is the mixed classification loss, so the first one in my list, then you can write this like this, and you can read it out as saying this is the probability of any two pairs not being equal. So, or the probability of a mistake, if you want, okay? So this is like the risk of making a mistake, and that's why people call this thing also the risk. So expected loss, expected risk, expected error are kind of the same name, they're different names for the same thing. All right, what do we want to do? We want to minimize, okay? Before actually discussing 1 minute what do we mean by try to find a good solution, we just want to observe one thing. If you hallucinate for a minute and assume that you have knowledge of this distribution, you can actually get some little more insight on the nature of the loss function and how it impacts the choice, the definition of the problem. In fact, typically, if you have to solve this problem, I can write it like this. So you have a function, but the function input is itself a function. That's what is called the functional. And how many of you know how to minimize a functional? Yeah, usually that's the percentage, like 3, okay? Well, why? Because it's a bit more complicated. Yes, they're functions, you have to put a bit more structure, you have to think a second about what's going on. And we're going to discuss this. We're going to discuss it throughout the course because basically half of this course is about minimizing functional, okay? We have error functional, we want to try functions, and so we have to learn how to minimize them. Good news for you guys is that typically what we're trying to do is that we're going to try to replace the function with the vector. So that now I can ask the question, how many of you know how to minimize a function of d variables? And now everybody goes. That's what you study, right? You have a function of d variables and it's fine. And we're going to try to get back to that because that's what I assume everybody knows, unless this not raising of hands is real and then go away. But there is one thing, there is one cheating trick that we're not going to use for computation, but we're just going to use for theoretical reason. Here's the following observation. It turns out that you can write this integral like this. So you first take the integral with respect to x and then the rest. Of course, now you see one of my writing skills, which is start to squeeze things in an unreadable way. You see what I did? I just split the integral, so this is the loss, and this is the condition, this is the stuff before. This, of course, you can always do it. One thing that can be shown is that, you see, here I have to find a function. If now I look at the integrand, not the whole thing, but just the integrand, now f of x here is not a function anymore because I fixed x. When I look inside of the integral, I fixed x. So call this alpha. Then you basically have some function that depends on x, but it's just a function of a real random variable. Okay? Make sense? So I took the integral, I split it in two, and I look at the integrand. When I look inside of the integrand, I see that it's just a function of one variable. It's what sometimes is called the inner, sometimes called the inner risk or inner error. Notice that in general, the fact that minimizing over f or over alpha is equivalent is not obvious at all. But it turns out that under very general assumption, one can do that mathematically. Okay, so you can turn the study of this functional, which is complicated, to an actual study of a real valued function, which I guess assume it's something that you know. I'm not saying this because we're going to use it to design algorithm, but just because now we can ask the following question. If I fix a loss function and I don't know the distribution, but I assume that it's, I don't know the exact shape of the distribution, but I assume it to be known, so I can handle it as if it's known. Can I just derive the form of what you might want to call the minimizer, the minimizer of this? So not only the mean, but the argmin, okay? You want to know if you minimize this, and there is some function, let me call it f star, which is the best possible function. Might be one, might be many. How does it look like? Okay. Now we have some, this point of view allows us to reduce this question to a somewhat simpler term, because now you just have to minimize a real valued function. Suppose that we achieve this, what we're going to find out? Well, whatever we found out is going to depend on the loss and the distribution. So it's going to be as useless as the problem originally, because we don't have the distribution. It's going to be hard to compute. But at least we would be able to see if it makes any difference to choose a loss function or another, because it will depend on the loss function. For example, we can ask, what is the target function? This is the name I want to give to this guy. If you take the square loss, okay? So take V A to be just A squared in that definition over there, okay? Regression, you know, just try to minimize this. To go here, right here, the integral is d of rho y given x. This become y minus alpha, because that's what I did. I want to replace the second entry with just a generic number. And then I just want to take, you know, there is a square here. Now I just want to with respect to alpha and set it equal to 0. Again, what I'm doing here, I want to try to look at the minimizer of this. Now this is complicated, so I use this property, it's called Aumann principle, that tells me that sometimes I can, under weak assumption, look at the minimum integrand, so that now I can just take derivatives. And now I pick an example. I have to pick an example. I take the square loss. I plug it in here. This is just a function of one variable, and now I can just minimize it. Okay. What do you get? If you do a bit of calculation, you find out that this is an easy case. It's differentiable, smooth, convex, whatever. And it turns out that alpha, which is nothing but star x, if you want, is just equal to the rho of y given x, y. Okay? You can almost do it with your eyes. This is what is called the regression function. It's the average of all the outputs. So if you take this plot, it says if I have not one value here, but the whole distribution of possible values, and I do the Gaussian thing because it's the only one I can draw, I'm going to try to say that the best thing, if you give me that distribution, which in practice you don't have, is to pick the average of all those values. And that's the ideal thing. That's what the least square is doing for us. Okay? What if you were taking, does it make sense? Cheating here. This is just a, what you might call an information theoretic or a decision theoretic point of view. I'm assuming that I know the distribution, and I just want to look at a quick effect of my loss function. What if I was to take not the square loss, but rather the absolute value? Would I get the same thing? In general, no. And in fact, you don't. And I guess this might be actually a piece of a problem set. What you get is actually the median of the distribution of the outputs. So the one point that splits the distribution into equal parts with equal mass. Okay? You can keep on going and check what happens if you do this. Now, this is the case of regression. And so the take-home message here is, if you were to take a look of the minimizer of the true risk, the one the one that you call the target function, because that's your target, you will find out that depending on the loss function you choose, you get a different solution. Okay? By choosing a loss function, you're actually choosing a different problem. And it's fine, because it actually was defining a different problem. It was one of our two ingredients. Okay? What about classification? Suppose that I do the same thing, but I actually assume that the output y is just plus or minus 1, okay? Then this expression is come out of an overshoot because this is a much simpler situation. This integral, so this is the sum of all the possible y's with their probability. Okay, but how many y's I have? 2, 1 or minus 1. So I can just write this as, rho of y given x minus rho of minus y given x. Okay? And then if you want, I can just say, okay, but this guy is actually 1 minus this guy. Okay? These two probabilities sum to 1. But it doesn't really matter. Let's just look at this. Okay? So you get this. Okay? And then you say, okay, how is this related to, does it make sense for classification? The interpretation of this is that I take the output, and then for each x, in this case, I have that for each x, I get a whole distribution of values, and then I take the mean of the distribution. And again, don't be misled. I always write Gaussian because I have a small brain, and it's complicated to think about something else. What about classification? And that's not really how, that's not really a useful interpretation. Why would it make sense? You actually have this difference. This difference really kind of makes sense. Somebody was saying, typically what you do in this case, when you solve a problem where you would want to predict 1 or minus 1, actually predicts the real values, then what do? You take the, why would you take the sign? Why is that a good idea? Just because somebody told me? Well, actually, if you take this point of view, what is the sign of this? Which of the two probabilities is bigger than the other? So it makes a lot of sense, okay? You're just basically taking, if I could solve the problem exactly, I would find the difference between two probabilities. And then I want to check which one is bigger, and I would go for that, okay? Indeed, if you were to do exactly this calculation, but rather than the square loss, we're taking the misclassification loss, which again, it's a crazy non-convex loss function. We'll find out that it approximates not the difference of the probability, but its sign. Is actually solving the problem exactly. It finds exactly the sign. So you see that what I did by choosing the square loss is that I did a relaxation. I had binary functions. I actually allow myself to look for real valued functions. And then what I do is that I'm not getting a Boolean function. I get something which is related to the Boolean function I should shoot for. You can play the same game for each of this. You will, because it's a problem set. And it turns out that the logistic is similar, is estimating in some sense, the conditional distributions of the two classes. The hinge loss is some kind of magic. And it's one of the reasons why is actually a good loss for classification. It's not, you see, this tells you that this is a perfectly fine loss for classification. Okay? There's one point of view that says this is perfectly fine. It's just shooting for a condition, take the sign, why not? You have to provide me a reason why, because for now we just have a misleading plot. Yet it feels that this one should be better, okay? It feels better, just intuitively. Well, what you can check is that if you do that calculation, you don't get the conditional distribution, but you actually just really get the sign here. So if you take the hinge loss returns a Boolean function. So it has the same target as the misclassification loss. Now it's 227, so this might not be the friendliest piece of information I gave you today, but it's actually kind of interesting. There is a problem set to appreciate this. Even if you relax the problem and go from Boolean function to real function, this one loss function doesn't really care and spit out, ideally, a Boolean function. So in some sense, it shows that it's a tight relaxation of the problem, okay? That it's somewhat a closer relaxation of the problem. Okay? So let me use the last 3 minutes because we started 5 minutes late. No, 2 minutes because I think it's illegal to use them all. I just want to make 2 comments, okay? Appreciate how I spoke absolutely nothing about algorithms, so it should be refreshing if you're used to an algorithmic course. I left out the question of, okay, but so which loss function should I use for classification? Because for regression, you change the problem. For classification, they seem to all shoot for the same guy. So you might want to think about this question when you are riding back home tonight. And What we're going to do next is basically try to set up, the stage to how we build algorithms. And the first thing would be to be able to handle functions. This function class will not be particularly useful for any practical purpose. So today, the whole goal was just to explode this into actually meaningful objects, okay? And what we want to do next is start to see how would you solve this problem, okay? What's needed to solve this problem? All right, I'm all set. I would say go, and if you have questions, I'll take them offline.